Hi, my name is Ashwani Kumar. In this video, we are going to see the introduction of the electrostatics and whatever the laws applicable to this one. So both these two we will say in this video. Here the electrostatics. That means before going into the electrostatics, we have to discuss about the electric dipoles and the charges, different types of the charges and flux lines, and what is the direction of the flux lines, and what is the electric flux density, and what is the electric field intensity. So all these things we are going to see one by one. So first of all, electric charges. Generally, we are having the dipoles. Okay, a dipole. So if you are talking about the electric dipoles are positive and negative. That means positive charge and the negative charge. And while coming to the magnetic dipoles are north pole and south pole. Okay, so these are the dipoles. And now while coming to the electric charges. Okay, so in this topic we are going to discuss about the electric dipoles in the electrostatics. Okay, so coming to the positive charge. So if you are taking the positive charge, then surrounding the charge, few flux lines will be there. So if it is a positive charge, then the flux lines flows outwards. This positive charge, that is a property of this one. Okay, outward the positive charge. That means if you are taking the positive and negative combinedly as an electric dipole, that means let's take the two plates. Connect the plate 1 to the positive terminal of the battery and plate 2 to the negative terminal of the battery. So now this plate becomes a positive because it is connected to the positive terminal of the battery, and this plate becomes a negative because it is connected to the negative terminal of the battery. And in this case, the electric flux lines will produce, okay, and these electric flux lines will always flows from positive to negative. That means away from the positive and towards the negative. Okay, so it is the direction of the electric flux lines. The same case here, I isolated both these two electric dipoles. Isolated means here I am talking alone only about the positive charge. Okay, and next I will take the alone negative charge. But from this concept, you can understand what is the direction of the flux lines if you are taking alone one individual either positive charge or the negative charge. So as you all of you know that the electric flux lines always flows from positive to the negative charge in the electric dipoles, and the magnetic flux lines always flows from north pole to the south pole. Okay, so while coming to the magnetic flux lines, we cannot able to separate the north pole and south pole. That means we cannot able to isolate, that we will see in the next lectures. But while coming to the electric dipoles, here we are going to discuss about the individual positive charges and the individual negative charges. That means the isolated charges. Okay, so while coming to the semiconductors, we are going to discuss about the holes are having the positive charges. That means holes can be considered as an example for the positive charge carriers, and electrons can be considered as an example for the negatively charged carriers. Okay, so if I'm taking the positive charge carrier or the positive charged particle, let's take it is a Q1. Q1. That means here the Q1 is a positively charged particle, and here the flux lines are away from this positive charge. If you see here, the flux lines are away from the positive charge and towards the negatively charged one. In the same case, if I take here the negatively charged particle, let's take, I'm naming this negatively charged particle as a Q2. Now whatever the flux lines are there, the flux lines are towards the negatively charged particle. Okay, so like this. And if you're taking the positive charged particle and negative charged particle with some distance, then the flux lines are continuity here. The flux lines are flowing from positive charged particle to the negative charged particle. So just like this, whatever this example I shown here. Okay, and whatever the arrow marks I drawn here, these arrow marks are called as a flux lines. Flux lines. So flux lines are the main responsible to produce any one field. If the electric charged particles are there, that means the positive charged particle or the negatively charged particle, then the electric flux lines will produce, which leads to the development of the electric field. In the same case, if you're taking the magnetic dipoles, then the flux lines, those are called as a magnetic flux lines, which are flowing from north pole to the south pole and which are responsible for the production of the magnetic field. Okay, so here before going into the electric field, first I'm going to say you about the electric flux density. So generally the amount of flux is going to be represented with this symbol that is called as a psi. And if I'm taking one unit area box, okay, so if the flux lines are producing, that is away from the positively charged particle in the free space, and here I'm taking in this free space I'm taking certain area, and this area of this box is a 1. Okay, so let's take 1 meter square. Okay, and how many number of flux lines are there in this unit area, that is called as a flux density. That flux density is represented with the capital D. That means capital D can be called as a number of flux lines per unit surface area. Fine. Number of flux lines per unit surface area is called as a flux density. So based upon this definition, whatever the definition I told for the electric flux density, that is capital D, the number of flux lines per unit surface area, or else the rate of change of flux lines per unit surface area. Okay, both these two can be called as a electric flux density. That means this statement can be written in mathematical as the rate of change of flux density with respect to the unit surface area. Okay, or else the number of flux lines are flowing through the unit surface area. Okay, flux lines, generally flux is represented with the psi per unit surface area, and from this expression I can write that d psi is equal to capital D into ds, right? And if I integrate both these two sides, then here integration and differentiation gets cancels. Now the electric flux, that is psi, is equal to integration of d into ds. That means surface integral of the electric flux density becomes is equal to psi. Okay, so we can say like this. It is one formula that you have to remember in front to understand about the Maxwell's equation. Fine. And again, if I take the ratio of the electric flux density and the permittivity of the space, okay, permittivity of the space, that means if this positive charge is kept in any one free space, then here epsilon represents the permittivity and epsilon naught represents the permittivity of the free space, and epsilon suffix r represents the permittivity, relative permittivity of any certain medium or the material. Okay, so if it is a free space, then I can write that d divided by epsilon can be written as a epsilon naught. And if this positively charged particle is kept in any certain material, for example, let's take, if you're taking the copper wire, in the copper wire the electrons are flowing generally, right? That means the flowing of current will be there. So if the electron is flowing in this one, that means electron is a negatively charged particle, right? That means the electric flux lines are towards or inward this negatively charged particle. And now this one, the epsilon, that means the permittivity of this one can be represented as electric flux density divided by epsilon naught into epsilon r, where epsilon naught is a permittivity of the free space and epsilon r is a relative permittivity of this material. That is, if it is a copper wire, then you can take the relative permittivity of a copper. Okay, so like that, epsilon naught is nothing but a constant, and while coming to the epsilon is nothing but a relative permittivity that depends upon the type of a material in which the charged carriers are flowing. And coming to the constant, that is epsilon naught, can be given as 8.85 into 10 power minus 12 Faraday per meter. So it is a constant, that is permittivity of the free space. And while coming to the epsilon r, that is relative permittivity changes based upon the different materials, but while coming to the relative permittivity of the air is 1. So it is very important as per our UGC NET exam. Relative permittivity of the air becomes is equal to 1. So that's why whenever we're taking the epsilon, that is the permittivity in a free space. So permittivity in a free space means generally the formula to the epsilon is epsilon naught into epsilon r. But if you are taking a free space or air, then epsilon naught becomes is equal to 8.85 to 10 power minus 12 Faraday per meter, but epsilon r, that is relative permittivity of the air, becomes is equal to 1. So 1 into epsilon naught becomes is equal to epsilon naught. That's why if the medium is the air or the free space, we are taking simply epsilon as a epsilon naught. Okay, that means epsilon r becomes is equal to 1 here. That is the in-depth meaning of this one. So remember this one, the relative permittivity of the air becomes is equal to 1. And why here I am speaking about the ratio between the flux density and the permittivity is that the ratio between the flux density and the permittivity becomes is equal to electric field intensity or electric field strength, which is represented with the capital E. And now the D, that is electric flux density, can also be given as epsilon into capital E, or else completely it can be given as, where epsilon is can be given as a relative permittivity of the free space, sorry, permittivity of the free space into relative permittivity of the material into electric field intensity. So that means the electric field intensity can be defined as a ratio between the electric flux density and the permittivity. Okay, so like this, you have to remember the formula to the electric flux density with respect to the flux, and this flux becomes is equal, electric flux is equal to surface integral of the electric flux density, and permittivity is equal to multiplication of the uh, epsilon naught into and epsilon naught and epsilon r, and where the relative permittivity of the air becomes is equal to 1, and the permittivity of the free space is equal to, it's a constant, that is 8.85 to 10 power minus 12 Faraday per meter, and the ratio between the electric flux density and the permittivity is called as electric field intensity, or simply called as electric field or electric field strength. Anything is fine. So after going through all these things, and now while coming to the definition of the electrostatics, is nothing but electrostatics means these are some certain kind of fields. The field which exist due to the static charges. Static charges are slowly moving charges. Okay, both these two. That means the field exists due to the static charges or the slowly moving charges is called as a electrostatic fields. Here the name itself is there, electro plus static. Static is nothing but a which is not moving. That means if you're taking the positive charged particle or the negatively charged particle, the field which is existed by this static charges or the very slow moving charges is called as a electrostatic field. So it is an introduction to this electrostatics once, and while coming to the next video we are going to see the Coulomb's law and the Gauss law, which are really important for this electrostatics. Thank you.